Alrighty, kiddos, welcome back. We'll be wrapping up section 4.3 on differential equations today, looking specifically at two application problems of differential equations, where in the first, we're going to look at a rectilinear motion problem. Given the velocity of a particle along a line, can we determine the equation that governs its location or position? And then the second problem is throwing a ball up in the air. If we know the initial velocity, we're going to see that because the acceleration of any object around close to the Earth's surface is constant, we'll be able to do a similar thing, moving backwards with the antiderivative from the acceleration to figure out the velocity equation and then the position equation. So sort of continuing this theme of the antiderivative, the integral being the inverse of the derivative, meaning we can go backwards. So if the derivative allows us to kind of see how something is changing, going from the description of a quantity to how it changes in an instant, the antiderivative says, okay, if you know how something is changing, you can then use this technique of antidifferentiation to then move backwards up that chain to see, for example, if you know how a particle is moving, where is that particle at a given moment? So it's a pretty powerful thing to be able to do. And one of the big applications in real world uses of the integral is starting with knowing how something is changing, going backwards to how is the quantity actually behaving. So we will jump in with those two examples. We won't be terribly long, should go pretty quick. Then we'll be done with 4.3. We previously wrapped up example 2, where we were doing the antidifferentiation and then plugging in some initial conditions. And we're going to be doing something very similar with both of our examples. We're using some initial conditions about our system, whether it's rectilinear motion or a ball in motion upwards, using that coupled with our antidifferentiation to find some key information. So example, let's actually do we need a full page. Yeah, sure, why not? Let's just start this on a new page, fresh page. This is example number 4. So this will be rectilinear motion. And what we are told is a particle is moving on a line where v centimeters per second is the velocity of the particle at t seconds. And they tell us that v, the velocity of this particle along a line, is 10 times the cosine of 2 pi t. And it says if the positive direction is to the right of the origin and the particle is 5 centimeters to the right of the origin at the start of the motion, find its position when t is, and then they list off a bunch of values for t. We're going to kind of bypass that. You can do that on your own if you want, but we're just going to come up with, starting from this velocity, can we come up with the general equation for the position of this particle? And the answer is yes. Antidifferentiation gives us that ability. Let's note that that S is equal to 5. So the position is 5 when t is 0. That was what they told us, was the particle is 5 centimeters to the right of the origin at the start of the motion. Well, the start of the motion is t equals 0, or we're assuming that because we haven't been told otherwise. So what do we do? Well, first we remember back to rectilinear motion and remember that the velocity is the first derivative of the position. In other words, is the same as ds dt. So the derivative with respect to time of s, which is the position of our particle, is our velocity. And so now we can see where, okay, this technique of separating out this derivative, this differential equation, will allow us to solve and work backwards. And so separating this out, we end up with ds is equal to 10 times the cosine of 2 pi t dt. And now we have successfully separated this differential equation, only have s's on the left side, only have t's on the right side. So now we can just hit both sides with that integration symbol. And then this will allow us to move backwards and figure out, okay, well, the antiderivative of ds is s. So our position of our particle will be whatever this antiderivative ends up being. Now the book kind of just like blitzes through this. And if you're just kind of following along the book, it's not 100% clear where, well, it is if you're thinking how the book is thinking. They kind of just barge through a chain rule here. This is technically a composite function. Okay, the cosine of 2 pi t is a function. This is not just cosine of t, so it's not a simple matter of saying that the antiderivative is the sine of t, because it's not exactly true, because there's going to be some chain rule when you differentiate. And so there really is a u sub here. So I'm going to show the u sub where the book doesn't. The book just kind of like assumes that we're familiar enough with the chain rule now in reverse that we can do it without the u sub. I don't think we're there yet, so I think a u sub is an appropriate thing to do here. And so off to the side, we'll say that the u, again, is going to be our innermost guy. It's going to be 2 pi t, which means that du is 2 pi dt. Du dt would be 2 pi, and then separating that out, which means that dt is equal to du divided by twice pi. Du divided by twice pi. So making that sub, we have 10 times the cosine of u, and then dt is du over twice pi. And so this integral actually becomes, well, the 2 cancels with the 10 to give us a 5. We can pull that out now, the 5 over pi times the antiderivative of the cosine of u du. Okay, so now we can do this integral without worrying about the chain rule, because cosine of u du, the antiderivative of that, is simply the sine of u times this constant out front plus c, and then subbing back in for u, the position is 5 over pi times the sine of 2 pi t plus c. Okay. And so it's sort of just doing a quick check. If we were to differentiate this, the derivative of sine is of course the cosine, but because there's a composite function going on here, we'd have to use the chain rule. Differentiating 2 pi t busts out that 2 pi, which then cancels with our 5 over pi to give us 10, which is what we started out with, 10 times the cosine of 2 pi. Okay. Again, the book sort of just like, so you could do that without the u sub if you were confident enough in picturing that, like, okay, yes, I understand that this will create a chain rule situation, so I need something up front that will cancel when I do the chain rule and give me 10, which is basically what the book was expecting you to be able to see, and maybe you did. But when in doubt, use the chain rule. Sorry, use the u sub, which is a way to do the reverse chain rule. Okay, so here is our general solution to the motion. But of course, we've got this constant here that we don't really want. And so we're going to use this initial condition. Okay, this is a one parameter differential equation. And so we need one initial condition, which we have. And we know that s is equal to 5 when time is equal to 0. Well, sine of 0 is 0, so c is equal to 5. And the motion of that particle is governed by the equation s equals 5 over pi times the sine of 2 pi t plus 5. And so if we want to know where the particle is at a given time, we just plug that time in to this equation, and it'll spit out the location. Okay, so what we did here is pretty remarkable. We started out with how a object is changing, what its velocity is, and from that we were able to move backwards and figure out, okay, what does that mean about where it will be? So knowing how an object is moving, coupled with anti-differentiation, allows us to figure out where it is. And that's pretty cool, and that's pretty useful. Has lots of applications in physics and chemistry and all sorts of stuff. Okay? But knowing how fast something is moving allows you to determine where that thing is. Pretty cool. And then you are free to work through the remaining parts of this where you are just plugging in values of t. One thing I will point out before I move on is I think this is one of the first rectilinear motion problems we've seen with a trigonometric function as its position, which means I think in chapter 1 or chapter 2, whenever we saw this, they were all like cubics or quadratics or quartics, which meant that the motion was kind of like it would go and then turn around and then turn around once more and go off. This motion is actually going to keep going back and forth, back and forth, back and forth. Okay, it's going to have this periodic nature to it and keep going back and forth across the origin forever. So kind of cool. Okay, so that was example 4. Example 5, probably need more than space than we have here, but we'll just start here. I don't know why or how exactly this happened, but I feel like we didn't really do many or any, maybe at all, things being thrown up in the air problems first semester, and they definitely showed up in a couple sections. I might have just forgotten to do those examples, or you guys figured it out in the homework. But this idea of throwing an object up in the air and just figuring out its velocity, figuring out where it turns around, figuring out the max height, it's a pretty like bread and butter type calculus problem. So we're going to see that in example 5, but we're going to start from the very end, is knowing very little about the motion of this object. We're going to be able to start with the acceleration and move backwards towards figuring out where it is at a particular moment in relation to the ground. And that's all going to be based on the fact that acceleration due to gravity is constant, or close enough to constant that we can act like it is. So acceleration due to gravity is 32 feet per second squared, or 9.8 meters per second squared. But then here's the tricky part. Think about acceleration. Think about how gravity is acting on objects. The Earth is pulling things towards it. So acceleration is always going to be negative in terms of up and down. You throw something in the air, acceleration is always acting against it, pulling it back towards Earth. Okay. These are both negative quantities. So then for our particular example, we are told that you throw a stone vertically upwards at an initial velocity of 128 feet per second. Okay. Stone thrown upward at 128 feet per second. So the initial velocity is given to us. We already know the acceleration because it's constant. And we need to find three things. The max height, which is position. B, how long in air. So when does it hit the ground again? It's again going to be based on the position. We want to figure out when is position 0. Well, the time is 0, but then another time as well. And then finally, speed at the ground. So that's kind of a tricky one. So speed when it hits the ground again will be based on the velocity. I kind of put those in parentheses because what we have is the acceleration, and we also have at least part of the velocity. But from this acceleration, we're going to need to come up with equations for both the velocity to answer the third part and the position to answer the first two parts. I think this is part D. We're going to skip part C. So how are we going to do that? Well, we're going to start from the thing that's set in stone, no pun intended, which is the acceleration. So the acceleration of this stone, and in fact of any object that you might have in the air around the Earth, is negative 32. And then remembering back to, this relates to rectilinear motion, is true of rectilinear motion or this upward and downward motion, is that the acceleration is the derivative of the velocity. So this is going to be like a two-step anti-differentiation process. We're first going to separate this differential equation and say that dv is equal to negative 32 dt. Applying the antiderivative on both sides. The antiderivative of dv is v. The antiderivative of negative 32 dt is negative 32t plus c. So our velocity is equal to negative 32t plus c. We'll call this c sub 1. Well, we know what the initial velocity is. They told us that it was thrown upward at a speed of 100 and at a velocity of 128 feet per second at time equals 0. So this is sort of a branch off from the abstract example or the non-stone example we did, I think example 2. In that example, we went ahead and differentiated this and then kind of use C1 in that final example, and then we had two initial conditions, but you could do that. But we're just going to do that as we go. We're going to solve this C1 before we take this second antiderivative. So we know that velocity is 128 when time is equal to 0. Which means that that first constant is 128. Means that our velocity is in fact negative 32t plus 128. And we'll use that in a second. But we need to do this again because the velocity itself is the derivative of the position, otherwise known as ds dt. And so then we can separate this again and see that ds is equal to negative 32t plus 128 dt. Successfully separated, just s is on the left, just t is on the right. Antiderivative on both sides. The left side gives us s, the position. The right side, the antiderivative of negative 32t, should be something like negative 16 t squared. Quick check, yeah, that checks out. Plus 128t plus C2. Okay, so how do we figure out this second constant? Well, the second initial condition that is not explicitly given to us, but from the nature of the problem, we can discern that the position is 0 when t is 0, okay? Which is not technically true if you actually think about the nature of throwing a stone. It's probably going to be, 5 feet above the ground. But for the purposes of our model, we're going to say that it's 0. Okay, maybe you had a cannon or something that you put on the ground. I don't know. But for the purpose of solving for this, we're going to assume that s is 0 and t is 0, which means that C2 must be 0, which hopefully you don't have to see me do that. But s is 0, when t is 0, all this stuff goes away, C2 is 0. And so our position is just negative 16 t squared plus 128t. Let's kind of box up what we have. We have a velocity, we have a position, and we have an acceleration, sure. And now we can use these to find the three things that they asked of us: the max height, how long is it in the air, and at what speed does it strike the ground when it returns. Let's go ahead and flip the page to read those three questions. A is the max height. Well, we have the equation of position, okay? And I suppose we could plug that into our calculator and just trace it and find it. But we can also apply calculus here and understand that, okay, the max height is going to correspond to a very specific moment in the velocity of our stone. Think about when you throw the stone up. It has this initial velocity. The velocity is decreasing, 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 and then it hits the peak and it's at rest. There's a momentary instant, I guess that's redundant, there's an instant where the stone is not moving before it changes directions. Well, because the velocity is signed, that's going to correspond to the change between a positive velocity and a negative velocity, or otherwise known as when the velocity is 0. So when is velocity equal to 0? In other words, when is velocity? When is negative 32t plus 128 equal to 0? Well, that is exactly when t is equal to 4. So that is when we have our max height. What our max height requires us to plug this in for to our position. So time of max height. What we actually need, though, is s of 4, which is negative 16 times 4 squared plus 128 times 4, which comes out to 256. Do a mini conclusion here. The stone reaches a maximum height of 256 feet. And this occurs 4 seconds into its flight. Okay. Which takes us to our next question, which is, how long is this thing in the air? To me, the way that we should approach this as well, when is the position 0? Because when it's 0, the flight is over. Now we're going to see there's going to be 2 of these s equals 0 values. One's going to happen at the beginning, but then one's going to happen at the end. So we're going to be interested in the second value. We want to know when is negative 16t squared plus 128t equal to 0. Factor out a negative 16t, and you get that t minus 8 needs to equal 0. And so there are 2 values that make this 0 when t is equal to 0 and when t is equal to 8. Now obviously 0 is not the length or how long it's in the air. Doesn't make much sense. 8 is going to be the length of our flight. It takes 8 seconds for the stone to reach the ground. And then part D, they want to know what is the speed when it reaches the ground. Now, speed is an important word. Speed is a different word than velocity. So we'll get to that in a second. Speed upon impact. And I guess we'll get to it right now. What they're asking us for is the absolute value of the velocity when t is equal to 8. So we're using this information for part B, knowing that it's going to hit the ground at 8 seconds. And so what we want is the absolute value of velocity at t equals 8. Why the absolute value? Because velocity is signed. So we're going to get a negative velocity after that thing turns around, but they want the speed. How fast is it moving in absolute terms? And so we want, first, what is the velocity at 8 seconds? Well, it's going to be negative 32t, which in this case is 8 plus 128, which comes out to negative 128. But we want the speed, which is equal to the absolute value of v is positive 128. Not sure if you can hear our little nugget in the background. I'm a little fit. She's fed. She's trying to go down for a nap. Apparently she doesn't want to. The conclusion here is when the stone hits the ground, it is traveling 128 feet per second, which the astute observers among you might be thinking, oh, that's how fast it's moving when it left your hand. Which kind of makes sense, okay? You throw it up at a certain speed, it reaches its max height, and then it comes back down the exact same distance, the exact same time, it reaches that max speed and it returns. Okay? There's always those horror stories that you hear of somebody fires a gun in the air, it goes up, doesn't come straight back down, but comes down with enough speed to hit some innocent bystander at the top of the head, kill him. And you're thinking, well, it shouldn't be traveling that fast. Well, yeah, it's going to return at the same exact speed that it left the gun. Same thing here. Okay, so that is the conclusion of 4.3. A couple application problems of differential equations. As I said before, after 4.3, The remainder of chapter 4 kind of diverts off in a different direction, where the remainder of our chapter is going to be looking at the application of the antiderivative to look at areas, undercurves, and then volumes. So what we just did is very important, and it will show up on the AP test. But for the remainder of the chapter, the way that we are going to be using the antiderivative is a bit different. We're just a bit more focused on something else. So hopefully that went okay for you, and we will see you next time.